Let me ask you something. Imagine you are sitting in a control room watching a radar screen. Suddenly the system detects something moving toward you at incredible speed. At first you might think it is just another missile, something the defense system has been designed to stop. But then the computer starts updating the numbers, and that is when things become unsettling. The object is traveling faster than 5 times the speed of sound. It is not following the normal arc of a ballistic missile. And even worse, it begins to change direction while it is still moving at that unbelievable speed. Now here is the strange part I want you to think about. The reason this weapon is so difficult to stop is not some mysterious secret technology. The real reason is physics. Very simple physics. The kind of physics that you and I can actually understand if we slow down and look carefully at what the air is doing around something moving that fast. Let me start with a question for you. When you hear that something is moving faster than the speed of sound, what do you imagine? Okay? Maybe you picture a fighter jet screaming across the sky, leaving that sharp cracking sound behind it. That moment when an aircraft passes the speed of sound feels dramatic. Almost like a boundary in physics has been broken. For a long time, people believed that barrier was extremely difficult to cross. Engineers once thought airplanes might shake themselves apart if they tried to fly that fast. But eventually, humans learned how to build aircraft that could pass that limit. Today, many fighter jets can fly at twice the speed of sound, sometimes even faster. Now, here is the interesting part I want you to think about. Hypersonic speed is not just a little faster than that. It is something entirely different. When scientists talk about speed in the air, they often use a unit called Mach. Mach 1 simply means the speed of sound. At sea level, that speed is roughly 1,200 kilometers per hour. So if an aircraft is flying at Mach 1, it is moving exactly as fast as sound waves travel through the air around it. If the aircraft flies at Mach 2, it is moving twice that speed. Many modern fighter jets can reach somewhere around Mach 2 or Mach 3 under the right conditions. That already sounds incredibly fast when you imagine it. But hypersonic flight begins at Mach 5. That means the vehicle is moving 5 times faster than the speed of sound. And some hypersonic systems may travel even faster than that, sometimes approaching Mach 10 or more. Now, I want you to pause for a moment and really think about what that means for the air surrounding the vehicle. Because when something moves through the atmosphere at ordinary speeds, the air has time to move out of the way. The molecules of air shift aside smoothly, and the aircraft simply pushes through them. But as the speed increases, the air starts behaving very differently. When an object approaches the speed of sound, the pressure waves it creates begin piling up in front of it. That is what forms the shock wave that produces the famous sonic boom. The aircraft is essentially compressing the air so quickly that the disturbance cannot spread out ahead of it anymore. But when you go far beyond that speed, something even more interesting happens. At hypersonic velocity, the air does not just get pushed aside. It gets violently compressed. Imagine you are pushing a piston extremely quickly inside a cylinder. The gas inside that cylinder would heat up dramatically because the molecules are being squeezed together with enormous force. The same thing happens to the air in front of a hypersonic vehicle. The air becomes compressed so intensely that its temperature begins rising to extraordinary levels. And this is where the physics becomes fascinating. At Mach 5, Mach 7, or Mach 10, the temperature around the vehicle can reach thousands of degrees, not because the engine is producing heat, but because the air itself is being crushed and accelerated around the surface of the vehicle. The atmosphere that normally feels cool and invisible suddenly behaves more like an extremely hot fluid flowing around the object. Engineers designing hypersonic vehicles have to deal with this intense heating problem because ordinary materials would simply melt under those conditions. Now think about this from the perspective of you watching that object approach. A missile moving at those speeds is not just fast, it is interacting with the atmosphere in a completely different physical regime. The shock waves are stronger. The heating is far more extreme, and the forces acting on the vehicle are dramatically larger than anything experienced by conventional aircraft. In other words, the moment you cross into hypersonic speed, the rules of the game start changing. So when you hear someone say a missile travels at Mach 5 or Mach 10, I do not want you to think of it as just another fast airplane. I want you to imagine something moving through the atmosphere so quickly that the air itself begins transforming around it. The sky in front of that vehicle is being compressed, heated, and pushed aside with tremendous energy. And once you begin to understand that change in the physics of the air, you can start to see why hypersonic weapons create such a serious challenge for anyone trying to track them or stop them. Now that you and I have talked about what hypersonic speed really means, I want you to imagine something with me. Picture an object flying through the atmosphere at Mach 5, maybe Mach 7, maybe even faster. At first you might think the air is just something the missile passes through, almost like empty space. But the truth is the air becomes one of the most important parts of the entire story. When something moves through the atmosphere that fast, the air around it starts behaving in ways that feel almost strange. Let me explain what I mean. When an airplane moves through the sky at ordinary speeds, the air has time to flow smoothly around the wings and body. The molecules move aside and then close back together behind the aircraft. It is a fairly gentle process. But when the speed increases, the air no longer has enough time to move out of the way smoothly. Instead, the air begins to pile up in front of the vehicle. This compression creates what we call a shock wave. If you have ever heard a sonic boom, that sound is the result of this sudden compression of air spreading outward through the atmosphere. Now here is where things become much more dramatic. When the speed reaches hypersonic levels, the air in front of the vehicle is compressed so violently that the temperature begins to rise extremely fast. You might not expect air to become hot just because something is moving quickly through it. But this effect is actually a simple consequence of physics. When a gas is compressed rapidly, its temperature increases. The molecules collide with each other more frequently and their motion becomes more energetic. So imagine the nose of a hypersonic missile cutting through the atmosphere. The air in front of it is suddenly squeezed into a much smaller space. The molecules cannot escape quickly enough, so they collide with each other again and again. Every one of those collisions transfers energy. The result is heat, and not just a little heat. At hypersonic speeds, the temperature of the air surrounding the vehicle can rise to thousands of degrees. In some cases, the air becomes hot enough to glow. Now, I want you to notice something interesting about that. The missile itself is not producing this heat directly. The heat is being generated by the atmosphere. The air that normally feels cool and invisible to you is suddenly behaving like an extremely hot fluid rushing around the surface of the vehicle. Engineers sometimes describe this situation as the missile flying inside its own envelope of extreme temperature and pressure. But the story does not stop there. When the air becomes hot enough, something even more unusual begins to happen. The molecules of air start breaking apart and losing electrons. In other words, the gas begins to turn into plasma. Plasma is a state of matter where the atoms are partially ionized and the gas becomes electrically charged. You normally see plasma in places like lightning or inside the sun. But under the right conditions, it can also appear around objects moving through the atmosphere at extreme speed. This means that a hypersonic vehicle can actually be surrounded by a thin layer of glowing ionized gas while it flies. That layer changes the way radio waves and radar signals interact with the vehicle. Sometimes it can make tracking the object more complicated because the signals reflect off the plasma in unpredictable ways. But even before we think about radar or tracking systems, the simple physical reality is already remarkable. Think about what you are really seeing here. A machine built by humans is moving through the atmosphere so quickly that the air itself is being crushed, heated, and partially transformed into plasma around it. The sky is no longer just empty space for the missile to pass through. Instead, the air becomes an active and powerful force, interacting with the vehicle at every moment. So when you hear people talk about hypersonic flight, I do not want you to think only about speed. Speed is just the beginning of the story. What truly matters is what that speed does to the air around the vehicle. The atmosphere stops behaving like the gentle fluid we are used to and begins acting like something far more energetic and extreme. And once you understand how violently the air is reacting to that motion, you start to see why designing and controlling hypersonic vehicles is such a remarkable engineering challenge. Now I want you to follow me a little deeper into what happens when something moves through the atmosphere at extreme speed. In the last part, we talked about how the air in front of a hypersonic vehicle becomes compressed and heated to extraordinary temperatures. But once that heating becomes intense enough, the air begins to behave in a way that is even more unusual. The gas surrounding the vehicle can begin transforming into something called plasma. And this is where things start to become particularly interesting for you if you are trying to track or communicate with that object. Let me explain it in a simple way. Air is normally made of neutral molecules, mostly nitrogen and oxygen. Each molecule contains electrons that are bound to atoms. But when the temperature becomes extremely high, those electrons can be stripped away from the atoms. When that happens, the gas becomes electrically charged. You now have free electrons moving around along with positively charged ions. This mixture of charged particles is what physicists call plasma. It is sometimes described as the fourth state of matter. You actually see plasma more often than you might realize. Lightning is plasma. The glowing gas inside certain types of lamps is plasma. Even the sun itself is made almost entirely of plasma. But the important thing for you to understand here is that plasma behaves differently from ordinary air because it contains charged particles. It interacts with electromagnetic waves in ways that normal gases do not. Now imagine a hypersonic missile racing through the upper atmosphere. The air in front of the vehicle is being compressed so violently that its temperature rises high enough to start ionizing the gas. A thin layer of plasma can begin forming around the vehicle. This plasma does not necessarily look like a bright glowing flame all the time, but physically it acts like a cloud of electrically charged particles surrounding the missile as it moves. Here is where the problem begins if you are trying to track that object using radar or communicate with it using radio signals. Radar works by sending out electromagnetic waves that bounce off an object and return to the receiver. By measuring the time it takes for those signals to return, the radar system can determine the location and motion of the target. But plasma can interfere with electromagnetic waves because the free electrons inside the plasma respond strongly to those signals. When a radar wave encounters a layer of plasma, several things can happen. Some of the energy may be absorbed. Some of it may scatter in different directions. In certain situations, the plasma can even reflect the signal before it reaches the actual surface of the object. To you watching the radar screen, this can make the target appear less clear or harder to track accurately. The radar may still detect something moving, but the signal can become weaker or more complicated to interpret. This phenomenon has been known for a long time in aerospace engineering. In fact, it appeared as a challenge during the early days of space exploration. When spacecraft returned to Earth from orbit, they entered the atmosphere at extremely high speeds. During re-entry, the surrounding air became hot enough to form a plasma sheath around the vehicle. That plasma layer sometimes blocked radio communication between the spacecraft and mission control for several minutes. Engineers referred to this as a communication blackout. Now, I want you to notice the connection here. Hypersonic vehicles move through the atmosphere at speeds that can create similar conditions. The plasma layer surrounding them may interfere with certain types of tracking or communication systems. It does not make the vehicle completely invisible, but it can complicate the process of observing it accurately. So when people talk about the challenge of detecting hypersonic weapons, they are not only talking about speed. Speed creates heat. Heat can create plasma. And plasma interacts with electromagnetic signals in ways that introduce new uncertainties for radar and tracking systems. All of these effects come directly from the physics of extremely fast motion through the atmosphere. If you step back and think about it, the situation is quite fascinating. A missile moving fast enough through the sky can cause the air itself to change state and become a cloud of charged particles around it. That thin layer of plasma becomes part of the physical environment the vehicle carries with it as it travels. And for you trying to observe it from far away using electronic systems, that environment can make the problem of tracking the object much more complicated than it might first appear. Now, I want you to imagine something from the perspective of a military defense system watching the sky. Suppose you are sitting in a control center and the radar suddenly detects a missile launch somewhere far away. This is not a new situation. For many decades, countries have built systems designed specifically to detect and intercept ballistic missiles. Those systems rely on a fairly simple idea. If you can measure the path of the missile early enough, you can predict where it will go. Once you know that future path, you can launch an interceptor and try to collide with the incoming warhead before it reaches its target. The reason this works at all is because traditional ballistic missiles follow a very predictable trajectory. Earlier we talked about how those missiles behave like objects thrown through the air. Once the rocket engines finish their job, the missile simply follows a long curved arc through space. Gravity pulls it downward while momentum carries it forward. The path is complicated, but it is still predictable because the physics behind it is well understood. If your radar detects the missile early enough, computers can calculate where that arc will lead. Now here's the important part I want you to notice. That entire defense strategy depends on the assumption that the missile will continue following the same path it started on. The interceptor missile is not chasing the target directly. Instead, it is launched toward a point in space where the target is expected to be in the future. Everything depends on the ability to predict that future location accurately. But this is exactly where hypersonic weapons begin to create trouble for you if you are relying on those traditional systems. Many hypersonic vehicles are designed to maneuver during flight. Instead of following a simple ballistic arc, they can glide through the atmosphere and adjust their direction as they travel. Even relatively small changes in direction can have a large effect when the object is moving at extremely high speed. Let me give you an example to help you picture this. Imagine you throw a ball into the air. If the ball continues along the same path, you can predict where it will land quite easily. But suppose that ball could suddenly steer itself a little to the left or a little to the right while it was still flying. Even a small change would move the landing point a significant distance away from your original prediction. Now imagine that the ball is traveling several kilometers every second. A slight change in direction can shift its future position by many kilometers. This is exactly the difficulty facing missile defense systems when dealing with maneuvering hypersonic vehicles. The radar may detect the object and begin calculating its trajectory. But if the vehicle changes direction during flight, those predictions must constantly be updated. Each adjustment creates uncertainty about where the object will be. A few minutes later, the interceptor missile that was launched toward one predicted point may suddenly find that the target is no longer there. There is another detail that makes this situation even more challenging for you as the defender. Traditional ballistic missiles spend much of their journey high above the atmosphere. Hypersonic glide vehicles often travel much lower, moving through the upper layers of the atmosphere rather than through deep space. Flying lower means the object may appear on radar later in its flight, which reduces the time available to respond. Less time means fewer opportunities to calculate trajectories, launch interceptors, and correct for errors. So now you can see how several factors combine to complicate the defense problem. The object is traveling extremely fast. It may be surrounded by heated air and plasma that affects tracking signals. It can maneuver during flight instead of following a fixed arc, and it may remain lower in the atmosphere. Reducing the distance at which radar systems first detect it, each one of these factors alone would make interception more difficult. When they occur together, the challenge becomes far greater. What fascinates me about this situation is that once again, the explanation comes back to basic physics. Speed changes how the air behaves around the vehicle. That environment allows new types of flight paths that were not possible for older missile designs. And those new flight paths break the assumptions that traditional defense systems were built around. The technology may seem very advanced, but underneath it all, the story still comes down to motion, energy, and the way objects move through the atmosphere when they are traveling unbelievably fast. Now, I want you to imagine the moment a hypersonic weapon actually begins its real journey. Many people think a hypersonic missile simply launches from the ground and flies directly to its target at extreme speed. But the interesting part is that many of these systems use a clever trick involving two different stages of flight. The first stage looks very familiar to you if you've ever studied ballistic missiles. A rocket launches from the ground and accelerates upward with tremendous power. Its only job is to push the payload high into the atmosphere and give it an enormous amount of speed. But once that job is finished, something different begins to happen. Instead of sending a warhead along a long ballistic arc through space, the rocket releases something called a glide vehicle. At that moment, the rocket stage separates, and the glide vehicle continues forward on its own. But unlike a typical ballistic warhead that simply falls back toward Earth, this vehicle begins moving through the upper layers of the atmosphere in a controlled glide. And this is where the physics becomes very interesting for you to think about. Let me give you an image that might help you picture what is happening. Imagine throwing a flat stone across the surface of a lake. If you throw it the right way, the stone does not immediately sink into the water. Instead, it skims along the surface, bouncing and gliding forward again and again before finally losing energy. In a very rough way, a hypersonic glide vehicle behaves somewhat like that stone, except it is not skipping across water. It is gliding through the thin upper layers of the atmosphere at extraordinary speed. The key idea here is lift. Even at hypersonic speeds, the shape of the vehicle can generate aerodynamic lift as air flows around it. The vehicle is designed so that the airflow creates forces that help support it in the atmosphere rather than allowing it to simply fall downward. By adjusting its orientation slightly, the vehicle can maintain a long gliding path while gradually descending toward its target. Now, I want you to notice something important about this, because the vehicle is gliding rather than simply falling along a ballistic arc. It has the ability to change direction during flight. Small adjustments in the angle of the vehicle can shift the direction of the aerodynamic forces acting on it. That allows the glide vehicle to steer slightly left or right, or even adjust how quickly it descends. These changes may not look dramatic, but when the vehicle is traveling at several kilometers per second, even a small steering motion can move the future path by a large distance. This gliding motion also keeps the vehicle within the upper atmosphere instead of sending it far into space. That means the vehicle can remain in a region where aerodynamic forces are still strong enough to influence its motion. Instead of following a predictable ballistic curve, the glide vehicle travels along a long, shallow path that can stretch across thousands of kilometers while gradually descending from the perspective of you trying to track the vehicle. This creates a much more complicated problem. The path is no longer determined only by gravity and momentum. Aerodynamic forces are constantly interacting with the vehicle, and the vehicle itself can make small adjustments that alter its trajectory. Predicting where it will be several minutes in the future becomes far more difficult. There is also another fascinating aspect of this design. Because the vehicle is moving through the atmosphere at hypersonic speed, it continues generating the intense heating and shock waves we talked about earlier. The air around the vehicle becomes extremely hot and compressed. And in some cases, plasma may form around it as well. So while the vehicle is gliding and maneuvering, it is also surrounded by an environment of extreme temperature and pressure created by its own motion. If you step back and think about the whole system, the trick becomes clear. A rocket provides the enormous burst of energy needed to reach hypersonic speed. Then the glide vehicle takes over and uses the atmosphere itself to continue traveling long distances while maintaining control over its path. Instead of a simple ballistic fall, the weapon becomes a fast-moving glider skimming through the edge of the atmosphere. And for you trying to predict exactly where that glider will go next, the problem becomes far more complex than tracking a traditional missile following a fixed arc through space. Now, I want you to think carefully about one simple thing: speed. Up to this point, we have talked about shock waves, plasma, light vehicles, and maneuvering paths. But underneath all of those ideas, there is one factor that quietly controls everything else. That factor is velocity. When an object moves through the atmosphere at hypersonic speed, the entire situation begins to change, because time itself starts to behave differently for you if you are trying to respond to it. Let me show you what I mean. Imagine an ordinary aircraft flying toward a target at about 900 kilometers per hour. Radar systems can detect that aircraft from far away, and the defense system has a comfortable amount of time to react. The aircraft might take an hour or more to reach its destination, depending on the distance. During that time, you can track it, analyze its path, and decide what action to take. Even a supersonic fighter moving at Mach 2 or Mach 3 still takes a significant amount of time to cross large distances. Now compare that with something traveling at Mach 10. Mach 10 means roughly 10 times the speed of sound. Depending on altitude, that can be more than 12,000 kilometers per hour. At that speed, the object is covering several kilometers every single second. I want you to pause and really think about that number. In just 1 second, the vehicle may travel the entire length of a large city. In 1 minute, it can cross hundreds of kilometers. What this means for you as a defender is that the timeline of events becomes extremely compressed. The moment a hypersonic vehicle is detected, the clock is already moving very quickly. Radar systems must identify the object. Computers must estimate its trajectory. And commanders must decide how to respond. All of this must happen within minutes, sometimes within only a few minutes. And remember that the object may still be maneuvering while all of this is happening. That means the predicted path you calculated 30 seconds ago might not be perfectly accurate anymore. The faster the object moves, the more sensitive those predictions become. A very small change in direction can shift the future position of the vehicle by many kilometers within a short period of time. There is another interesting piece of physics hidden in this situation that I want you to notice. When an object is moving extremely fast, its kinetic energy becomes enormous. The formula for kinetic energy includes the square of the velocity. That means if you double the speed, the energy does not simply double, it increases by 4 times. So when a vehicle is traveling at hypersonic speed, even a relatively small mass can carry tremendous energy simply because it is moving so quickly. For you trying to intercept that object, this creates an additional challenge. The interceptor missile must reach a similar region of space and collide with the target at exactly the right moment. But the target is traveling several kilometers every second, and the interceptor must accelerate quickly enough to match that encounter. Any delay in launching the interceptor reduces the time available to reach the interception point. Think about the timing for a moment. The radar detects the object. Computers begin calculating possible trajectories. The defense system decides to launch an interceptor. That interceptor must accelerate upward, climb to the correct altitude, and guide itself toward the predicted meeting point. Meanwhile, the hypersonic vehicle continues racing forward, covering enormous distances every minute. You can see why speed changes the entire nature of the problem. It reduces the time available for observation. It increases the difficulty of predicting future positions. It demands extremely fast decisions from both machines and humans. And it forces any defensive system to operate under intense time pressure. What fascinates me about this is that the situation is not mysterious at all once you think about it carefully. It is simply the natural consequence of motion at very high velocity. When something moves that fast, distances shrink in terms of the time required to cross them. What might normally take an hour can happen in minutes. What might normally take minutes can happen in seconds. So when you hear people say that hypersonic weapons are difficult to defend against, the explanation does not require complicated theories. It comes back to a simple observation that you and I can understand easily. When an object is moving several kilometers every second, the window of time available to react becomes incredibly small. And when time becomes scarce, every part of the defense process becomes much harder. Now, after looking at all of this together, the shock waves, the heating, the plasma, the maneuvering flight, and the incredible speed, I want you to step back with me for a moment and look at the bigger picture. Because when people hear about hypersonic weapons, they sometimes imagine some mysterious futuristic technology that operates almost like science fiction. But the truth is something much more interesting. The reason these systems create so much concern is not magic or secret physics. It is actually the opposite. It is the result of very simple physical laws working together at extreme speed. Think about the first idea we discussed, motion. Once an object reaches hypersonic velocity, it carries an enormous amount of momentum. That momentum does not disappear suddenly. In the thin upper atmosphere, there is very little resistance to slow the object down. So the vehicle continues moving forward with tremendous energy, covering huge distances in very short periods of time. For you observing that object from the ground, it almost feels as if the sky itself has become smaller, because the object can cross it so quickly. Then there is the interaction with the atmosphere. Normally the air around you feels calm and invisible, something you hardly notice as you walk outside. But when something moves through that same air at several kilometers per second, the atmosphere becomes a powerful physical force. The air compresses violently, heating up to temperatures high enough to change the chemical structure of the gas itself. The molecules break apart, electrons are stripped away, and the air can transform into plasma. In other words, the vehicle is not simply moving through the atmosphere. It is actively reshaping the physical state of the air around it as it travels. Next comes the idea of aerodynamic control. Instead of following a simple ballistic arc like older missiles, some hypersonic vehicles can glide through the upper atmosphere. By adjusting their orientation slightly, they generate lift and steer their path while still traveling at extreme speed. For you trying to predict where that object will go next, this introduces uncertainty. The trajectory is no longer a fixed curve determined only by gravity. The vehicle can modify its path, and even small changes become significant when the velocity is so high And then we return to the most powerful factor of all, energy. Kinetic energy grows rapidly with speed. When a vehicle is traveling several kilometers every second, even a modest mass carries enormous destructive potential simply because of its motion. That same speed also compresses the timeline. For anyone trying to respond, radar must detect the object quickly. Computers must estimate its path. And defensive systems must launch interceptors almost immediately. Every part of that process is racing against the clock. When you put all of these pieces together, the situation begins to make sense. Hypersonic weapons are not frightening because they break the laws of physics. They're frightening because they use those laws very efficiently. Momentum keeps them moving forward with tremendous energy. Aerodynamics allows them to maneuver within the atmosphere. Heat and plasma form naturally as the air reacts to the extreme speed. And the sheer velocity reduces the time available for any response. What I find fascinating is that every one of these effects can be explained using the same physical principles that scientists have studied for centuries. The equations describing motion, energy, and fluid flow are not new discoveries. They are the same laws that explain why a stone falls to the ground, why airplanes can generate lift, and why gases heat up when they are compressed. The difference here is simply the scale. When those familiar laws are applied to objects moving thousands of meters every second, the consequences become far more dramatic. So when you hear discussions about hypersonic weapons and the concerns they create, remember that the story is not really about mysterious technology. It is a story about physics. It is about what happens when human engineering pushes speed, energy, and motion into a regime where the atmosphere itself begins to react violently. And once you understand that, you begin to see that the fear surrounding these weapons does not come from the unknown. It comes from the very predictable behavior of the physical laws that govern our universe.